Did you hear about the physicist who broke up with gravity? They said it was pulling them down. Quite the jest, isn't it? We all have our own relationships with gravity. It keeps us grounded, quite literally. But in the grand theater of physics, gravity plays a role that is both fascinating and complex. It's a tale of unseen forces and ripples in the fabric of space-time, a tale of gravitational waves. But jokes aside, today we're diving into the intriguing world of gravitational waves. Imagine this. The year is 1916, and a man named Albert Einstein has just published his theory of general relativity. In the midst of a world at war, Einstein presents a radical idea that would forever change our understanding of the universe. He proposes that the force we perceive as gravity is actually the result of the curvature of space and time by mass and energy. This was a departure from the Newtonian concept of gravity, which had dominated scientific thought for more than 2 centuries. Einstein's theory also made a bold and controversial prediction: the existence of gravitational waves. These waves, he suggested, are ripples in the fabric of space-time, caused by the acceleration of massive objects. They travel at the speed of light, carrying with them information about their cataclysmic origins and the nature of gravity itself. But in 1916, this idea was met with skepticism. The technology needed to detect these minuscule ripples was simply beyond the realm of possibility. For decades, gravitational waves remained a theoretical curiosity, an elusive phantom of Einstein's mathematical framework. However, this did not deter a group of dedicated scientists who believed in Einstein's prediction. They embarked on a quest to prove the existence of these waves. It was a journey that would span a century, marked by countless setbacks, technological breakthroughs, and moments of sheer brilliance. In the 1960s, the development of laser technology opened up new possibilities. The concept of a laser interferometer, a device capable of detecting the infinitesimal changes caused by a passing gravitational wave, began to take shape. Yet even with this technology, the task was akin to measuring the distance to the nearest star, with an accuracy smaller than the width of a human hair. The following decades saw the establishment of massive interferometers around the world, the most famous being the Laser Interferometer Gravitational Wave Observatory, or LIGO. And so, after a century of doubting and research, in 2016, the existence of gravitational waves was finally confirmed. The announcement sent ripples through the scientific community, validating Einstein's theory and opening a new window into the cosmos. It was a testament to the power of human curiosity and the relentless pursuit of knowledge. So what exactly are these gravitational waves that took a century to discover? Let's dive right into it. Imagine throwing a pebble into a pond. The pebble disrupts the calm surface, creating ripples that spread outwards. Now picture the pond as the universe, and the pebble as a cosmic event, like the collision of 2 black holes. The disruption caused by this event sends out ripples, but these aren't ordinary ripples. They are gravitational waves. Gravitational waves are distortions or ripples in the fabric of space and time, a concept known as space-time. This idea was first proposed by none other than Albert Einstein in his general theory of relativity. According to Einstein, space isn't just an empty void, but a 4-dimensional fabric that can be pushed or pulled as objects move through it. So how do these waves come into existence? Well, when a massive object accelerates, like when 2 black holes spiral towards each other, it creates ripples in space-time. These ripples are the gravitational waves, and they propagate outward from the source, just like ripples on a pond. The more massive the object, the stronger the waves. However, unlike ripples on a water surface, gravitational waves stretch and squeeze space itself along with anything in their path. Imagine a rubber sheet being stretched and squished rhythmically, and you'll get the idea. But these distortions are incredibly tiny. We're talking about changes smaller than the diameter of a proton. Despite their minuscule size, gravitational waves carry with them information about their cataclysmic origins, as well as clues about the nature of gravity itself. They travel at the speed of light, unaffected by intervening matter, providing us with a completely new way of observing the universe. In essence, gravitational waves are like invisible messengers from the distant universe, bringing us whispers of cosmic events that would otherwise remain unheard. These invisible ripples in the fabric of space-time are not just theoretical predictions, they are real. Detecting these tiny ripples in space-time might seem like finding a needle in a cosmic haystack. However, it's not quite as impossible as it sounds thanks to some very clever technology and the work of dedicated scientists. Let's talk about the LIGO and Virgo observatories. Imagine two facilities separated by thousands of miles, each with two arms stretching out in an L shape. These arms, which are actually vacuum tubes, are each several kilometers long. Now, inside these tubes, a laser beam is split and sent down each arm. When the beams return, they should, in theory, meet back at the same point at the same time, creating an interference pattern of light. However, if a gravitational wave passes through, it will slightly stretch one arm and compress the other, causing the beams to return at slightly different times and changing the interference pattern. This method, known as laser interferometry, allows scientists to measure the incredibly tiny distortions caused by passing gravitational waves. Now you might be wondering, how small are these distortions we're talking about? Well, to give you an idea, the distortions caused by a gravitational wave are smaller than 1/10,000th the diameter of a proton. That's right, we're measuring changes smaller than the smallest things we know. And yet, despite the mind-bogglingly small scale of these distortions, in 2016, scientists at LIGO made history. They detected gravitational waves from a binary black hole merger over 1 billion light-years away. These were waves caused by two black holes, each with masses about 30 times that of our Sun, spiraling into each other and merging into a single, even larger black hole. The energy released in this event was so colossal that it caused ripples in space-time that traveled all the way to Earth and were picked up by LIGO's detectors. This was no easy feat. It took decades of theoretical predictions, technological development, and meticulous data analysis to make this detection possible. But the results were well worth the effort. The detection of gravitational waves opened up a new way for us to observe and understand the universe. It confirmed Einstein's century-old prediction and marked the beginning of a new era in astronomy. This was a groundbreaking discovery, a testament to human ingenuity and perseverance. It's a beautiful example of how, by pushing the boundaries of what we know and can do, we can uncover the secrets of the vast, mysterious cosmos we live in. So, we have detected gravitational waves. But why does it matter, you may wonder? Well, to put it simply, gravitational waves provide a whole new way to observe the universe. They are like the cosmic equivalent of a new set of eyes, allowing us to perceive aspects of the universe that we previously couldn't. Imagine being able to hear a symphony for the first time, after only being able to see the orchestra play. That's the kind of shift we're talking about here. Gravitational waves provide us with a new spectrum, a new wavelength to understand the cosmos, but there's more to it. They not only give us a new perspective, but they also allow us to study objects and events which are otherwise invisible. Consider the enigmatic black holes, for instance. These celestial bodies are so dense and have such strong gravity that nothing, not even light, can escape them, rendering them invisible to traditional methods of observation. However, when two black holes merge, they create ripples in the fabric of space-time, producing gravitational waves. By detecting these waves, we can study black holes in ways we never thought possible. Similarly, neutron stars, the dense remnants of collapsed stars, are also difficult to study due to their incredibly small size and extreme density. But when two neutron stars collide, they too create gravitational waves. Detecting and studying these waves can reveal invaluable information about these elusive celestial bodies. Gravitational waves are like whispers from the universe, telling us secrets about its most mysterious inhabitants. They are the cosmic messengers carrying tales of events that happened billions of years ago, in corners of the universe far, far away. In essence, gravitational waves have revolutionized our understanding of the universe. They have opened up a new realm of astronomy, enabling us to explore the cosmos in ways we could never have imagined. Gravitational waves have opened a new window to the universe, allowing us to see things we could never see before. The universe is no longer a silent movie, it's now a symphony, and we've just started to learn how to listen. As we stand on the brink of this new era of gravitational wave astronomy, we can't help but wonder what the future holds. The next chapter in our cosmic saga is set to be an exciting one as we push the boundaries of our understanding and venture deeper into the unknown. Just imagine the possibilities. We may uncover secrets of the universe that have long been veiled in mystery, perhaps even answering questions about the nature of dark matter and dark energy. We might detect gravitational waves from phenomena we've yet to even imagine, opening up a whole new realm of physics. Yet, as we reach out into the cosmos, peering into the fabric of space and time, there remain unanswered questions. How will these discoveries change our understanding of the universe? What new questions will they raise? What new challenges will they present? As we continue to explore the universe through this new lens, one question remains. Are we ready for what we might find?